frame with the wave speed, the Eulerian pattern will become stationary. Let's do this and indicate the translation velocity by an arrow at the bottom. Now let's resolve the velocities into components. The horizontal component is the velocity with which our frame is translating. The other component is the material point velocity in the original frame of reference. Let's see that catch up again. The path lines, which are also streamlines in this frame of reference since the flow is steady, resemble the form of the free surface. As a material point passes through each laboratory point, its velocity is instantaneously the same as that of the laboratory point. It is partly this possibility of eliminating one of the variables in the analysis, time, that makes the Eulerian representation more attractive. Most laws of nature are more simply stated in terms of properties associated with material elements, Lagrangian quantities. But it's nearly always much easier mathematically, when describing a continuum, to deal with these laws in laboratory coordinates. Thus, to write our conservation equations, we have to talk about transforming from one set of coordinates to the other. Let's talk first about the relation between time derivatives in a scalar field. Let us imagine a river in which a radioactive tracer has been distributed. Since we're interested in local changes, let us look at an infinitesimal part of this river. Now let us imagine that the tracer is suddenly and uniformly distributed in the river. These dots that are gradually disappearing symbolize the tracer, which is gradually decaying everywhere. These filled-in circles represent two laboratory points, which are infinitesimally close together on the same streamline, but which look far apart in our expanded view of the river. Since in this case we distributed the tracer uniformly, the radioactivity at the two laboratory points is the same, but is changing with time. We can add radiation counters at the laboratory points. The solid bars on these Eulerian radiation counters indicate the level of radioactivity at these two laboratory points. We can monitor the level experienced by a material point traveling from one laboratory point to the other by watching the open bar on the Lagrangian counter carried by it. The dashed bar represents the value recorded by the Lagrangian counter as the material point passed through the left-hand laboratory point. Comparing the before and after values of the Lagrangian counter, it is evident that the traveling point sees only the same change that each of the laboratory points sees. This can be written as the time difference multiplied by the rate of change with time. Suppose now, however, that the tracer is not uniformly distributed in the river, but that the intensity is greater upstream. Now the intensity at the downstream point is initially lower, and of course both are decreasing with time as before. Just as before, the only change experienced by the material point is due to decay. The change seen at a laboratory point is not, however, since new material of originally higher intensity is being swept past. To express the change experienced by a material point in Eulerian variables, we need two terms: the change of intensity with time at a fixed point, and the intensity difference between laboratory points at a fixed time. The total change when the material point has reached the right-hand laboratory point is given by the difference in level between the dashed counter on the left and the Lagrangian counter. The change with time experienced by either laboratory point is given by the difference in level between the dashed counter and the Eulerian counter on the left, and can be written, as before, as the time difference multiplied by the rate of change with time. The change due to the intensity difference between the laboratory points at any time is indicated by the difference in level between the two Eulerian counters, and can be written as the distance traveled multiplied by the spatial gradient in the direction traveled. The distance traveled can be written as the time difference multiplied by the magnitude of the velocity. The total change is the sum of the two changes described. The material or substantial derivative is the name given to the expression multiplying the time difference. This is simply the rate of change with respect to time seen by the material point as it passes the laboratory point, expressed in laboratory coordinates. Since it's to emphasize that the material derivative is the rate of change seen by a material point as it passes a laboratory point, but expressed in laboratory coordinates. In vector notation, the velocity times the gradient in its direction can be written as the scalar product of velocity and the gradient. We're also interested in the material derivative of a vector field such as the velocity. We're especially interested in that because the material derivative of the velocity gives an expression for the acceleration in a form which we need for the momentum equation. The expression that we just obtained for the material derivative of a scalar field would work just as well for each component of a vector field, but we can also show the material derivative of the vector field directly. Here are two laboratory points infinitesimally close to one another in a magnified view of an arbitrary steady flow. They lie on the same path line, and the material point is traveling from one to the other. The velocity of the material point is indicated by an open arrow attached to it. Clearly, although the flow is steady in the laboratory frame, the moving material point experiences change as it travels to regions where the steady velocity is different. The total change will be the difference between the velocity